All right. So can you hear me and see my screen?
Yes, sir.
Okay, great. So in the previous lecture, essentially the last thing we talked about was Slater's conditions to ensure strong duality. So we have not proved that it ensures strong duality. We just saw a couple of examples where Slater's conditions and Slater's refined conditions hold. So and and one particular thing we saw is in a convex optimization problem where the feasible set is a polyhedron, then the refined Slater's conditions are just immediately satisfied. So strong duality holds. So in the simplex method or the linear programming case is in fact a special case of convex optimization where the feasible set satisfies refined Slater's conditions. So if so I'm just going to restate that if the feasible set is a polyhedron and the objective function f naught is convex, the objective function is convex, then strong duality holds. That would be Slater's theorem, which is what we are going to prove today. Then strong duality holds. And we have noticed that even if you start with a non-convex problem, you always end up with a convex optimization problem for the dual. And we have not seen an like an example of that so far. Here, of course, to use Slater's conditions, you start with the assumption that f naught is convex. And in fact, one of the remarks we had made that any sub-level set of a convex function, if we are looking at things of this nature, this is always going to be convex. Like set of all x satisfying this if gi is so if gi is convex. And similarly, if um, hi is convex, then this will also be uh, yes. So this all right. So this is also going to be if this is affine. If hi are affine, I mean, if they are not affine, you cannot say that this level sets are in fact going to be convex. That's not going to happen. You can immediately see an example. You have a convex set, and you have this is the base space, and if I take a slice here, so it might resemble something like this, like a circle, which is not a convex set. But if I were talking about some level set like this, it will resemble the convex hull of this circle. But here we have assumed that the equality constants are based on affine conditions. So in that case, clearly it is both convex and concave. So this condition is a convex condition. So overall, the feasible set is convex. So the Slater's conditions are in fact is a very special case where the feasible set is convex and the objective function is also convex. But in that case, we know that or the claim is that strong duality holds. So this is clearly a generalization of the strong duality from the linear programming case. But the proof is going to be very, very similar. In fact, if we did the simplex method proof, we had remember we had done two proofs for strong duality. One of them was you looked at the final basis in your simplex method, the final basic feasible solution that you get, and based on that we had a formula for uh, so formula like how like for the cost function like c dot x, we had a formula for that. It was just a matter of moving things around and looking at the dual problem, and then it turned out to be equal. It was very much straightforward once you use the simplex method. But that proof will not generalize because simplex is very specialized to that particular case of a linear objective function. But the geometric proof that we did was using separating hyperplane theorem that will precisely like generalize. In fact, you just have to change a few words and the proof will just hold in this case. So in fact, you can say that like discovering Slater's conditions is more or less like looking at the geometric proof and seeing, okay, I mean, like how much can I push this proof further? Like how many conditions can I relax further so that this proof will still work, and that will give you Slater's conditions very naturally. So that's the important advantage of having different sorts of proofs. Those give you different points of views, and in general, like different point of view will give you different direction of generalization. All right, so let's get down to business. So just for your reminder, let me state Slater's theorem. So so for a convex optimization problem, that is both feasible set is convex and the objective function is a convex function. problem. If refined Slater's conditions hold, and what exactly are refined Slater's conditions? That is, we have, so there exists something in the domain. So there exists x tilde belonging to, so x tilde vec belonging to the domain of, belonging to omega, which is in fact intersection of the domains of the gi's I from 1 to m, intersection with intersection j equals 1 to p, domain of the hi. So remember, omega was not necessarily the feasible set. It was the domain on which all these objective functions and all these functions are defined. In fact, that is not included here. So let me include that here. Intersection domain of the objective function. So that is my omega, which is bigger than the feasible set. So there exists x such that it is in the interior of these inequality constraints, such that gi of x tilde this is strictly less than 0. So instead of being less than equal to 0, that is the definition of the feasible condition. So you have a feasible point which is strictly in the interior of the domain of these gi's. Okay, so that is one necessity. And for that particular point, you have the affine conditions. So HIs, these are affine functions, right? These are affine functions. And you have HI of x tilde vec is equal to 0. So here you have equality. Here you have strict inequality. So refined, so these are Slater's conditions, but refined Slater's conditions say that if Gi is an linear inequality constraint, you don't really demand the strict inequality. You don't demand like untightness, so to say. I mean, if it is tight, it is just fine for you. That is no condition at all. If Gi is a linear inequality constraint, we don't care whether it is less than, strictly less than 0, or we don't care whether Gi x tilde strictly less than 0 or not, or it is equal to 0. So with these refined Slater's conditions, the conclusion, there are two parts to the conclusion. First of all, the strong duality holds. That means if I take supremum, if I look at the maximization problem, like the dual problem, so maximization of capital F lambda nu, if you remember what the definition is, that is the Lagrange dual, and lambda is going to be positive and nu is free. It's a free kind of variable corresponding to the equality constraint. So the assertion is that that maximum is equal to minimum of your original convex optimization problem. But the additional thing is, and the dual optimum is in fact attained. So it's not just a supremum, it is in fact the maximum. And the dual optimum is attained. So this part. So these are the two assertions of Slater's theorem. If these conditions are satisfied, and like the first remark I made, if all the constraints are linear, like whether inequality or equality, they're all linear, in that case, refined Slater's conditions are naturally satisfied. So these are no conditions at all. So essentially, it is saying for a convex optimization problem with feasible set of convex polyhedron, the strong duality holds and dual optimum is achieved. All right. So now let's get on to proving this theorem. All right. So now what we'll do is try to construct two convex sets and kind of rephrase this as like a separation type of problem. So now look at this set A consisting of all points u, v, t. So essentially this will belong to Rm. This will belong to Rp. So M, remember, is the GIs, number of GIs. So I was going from 1 to M and J was going from 1 to P. And this T in fact belongs to R. This will be kind of corresponding to the value of the objective function. So all such u, v, t such that there exists X belonging to omega. Remember what is omega? Omega is nothing but intersection of these domains. So I'm not saying it is a feasible set. That is important to remember. Omega is intersection of domains of the objective function of the GI. And I should say HI, but HI is not important because it's an affine function. So the domain is all of Rn. So that's not really giving any restrictive condition on the domain. All right. So there exists X belongs to omega. So domain of F naught intersection with I equals 1 to M, domain of gi. Hi, again, I repeat, I don't include because these are affine functions whose domain is all of R. All right. So here we have g of x is less than equal to ui. So for I equals 1 to m. So these are I'm defining what you are allowed. So u vt, this is allowed in A if there is some x in this omega such that gix is less than equal to ui, that is the ith coordinate of this vector, and hi of x, this is an affine function. This is in fact equal to vi, or hj of x is equal to vj, where j is from 1 through p. And the third condition is the objective function is less than equal to t. So which point do we really care about? We care about 0, 0, and like for example, bit alpha star, right? If I put alpha star here, this will be in fact the empty set, because wherever we have x which is satisfying gix is less than equal to 0, hjx equals 0, there we know that the minimum of f naught is in fact going to be alpha star. That was our definition of the minimum. But yeah, if there is if t is strictly less than that alpha star, then this is an infeasible thing. So this will be an empty set. So this will be yeah. So this motivates us to define this other convex set, which is 0, 0, s. So this is again in the same space. We are in the space Rm cross Rp cross R. So we are in the Euclidean space R of m plus p plus 1. So this B we are defining as all those points 0, 0, s. So 0 vec. I should write 0 vec, 0 vec, s. S is a real number such that s is strictly less than alpha star. Now clearly A intersection B is equal to empty. That we can see because if there is some point in both B and A, let's say that point is 0, 0, whatever s, then what it is saying is gi of x, there is some x in the domain, so that gi of x is less than equal to 0, that is the vector u is 0, then hjx equals 0. So x actually in fact belongs to the feasible set. Not only is it in the domain, but also it's actually more restrictive. It is in the feasible set. But then we are discovering that f naught of x is less than equal to s, which is strictly less than alpha star, which is contradicting the very definition of alpha star. So there cannot be any two common points. And B, that B is convex is very trivial to see. It's just 0, 0, s. If I take convex combination, first two vectors will always stay 0. The third vector is defined by this condition, which is essentially a ray, which is a convex set, a ray in R. So with one endpoint alpha star. So B is convex is easy to see, and A is also in fact convex. So why is that? First of all, omega is convex because all of these are convex functions. These gi's are convex functions. F naught is a convex function. So omega is convex. So we defined on this. So x is defined on a convex. Okay, just let me say the domain is a convex set. And then when we are looking at this condition, these are all convex conditions. If I look at gix, I take some combination of x1 and x2. We have already seen that this is like a sublevel set. So if x1 satisfies these conditions, x2 satisfies these conditions, and so then t lambda x1 plus 1 minus lambda x2 will also satisfy this condition, and this is an affine condition. So anyway, that will be satisfied. And again, f naught is convex, hence this condition will also be satisfied. So we are here to show that A is convex. We are using strongly the fact that GIs are convex functions and F naught is also convex. So the conclusion is, since F naught and GIs are convex functions and HJs are affine functions. So saying that Hj is convex, like I had mentioned, does not suffice because it is an equality condition. Convexity will only give you inequalities. All right. Since all of these holds, we have that A is a convex set, in Rm cross Rp cross R. or R to the m plus p plus 1. In that Euclidean space, it's a convex set. Now we have two convex sets whose intersection is empty. By the way, so if you recall, our separating hyperplane theorem kind of said if you have two closed convex sets and so on, but actually it included this part that they are actually, it could be any convex set, because if they have some intersection, then it must only be on the boundary. For example, if I took two open balls, say, and they were like tangential to each other, if I remove the boundary, then I have A intersection B is empty. So this tangential hyperplane is also separating hyperplane. The fact is that it will contain points from both here and here, but it is still a separating hyperplane. So the more general separating hyperplane theorem says that if you have two non-intersecting convex sets, you will always have a separating hyperplane. Doesn't matter whether they're closed or not. If one of them is closed, other is a point, we had that strict separation and so on. But if you don't care about strict separation, just intersection being empty suffices. So that's the result we're going to use. So by the separating hyperplane theorem, we have a separating hyperplane which is defined by, let's say, h of lambda tilde vec nu tilde vec. And since this is going to be in Rm, so we're splitting up. Like generally we would say, okay, there is some vector in m plus p plus 1, and this separating hyperplane is normal to it. But here we're just splitting this up into three parts, comma mu. So this minus contains A, so contains B. So B is contained in this, and A is contained in H plus lambda tilde vec, nu tilde vec, and mu. So that's precisely the assertion of the separating hyperplane theorem. So there exists such lambda tilde, nu tilde, and mu. Okay. So just writing out, what does that mean? What does it mean to belong to this closed half space? It just means that if I take any point in B, the inner product should be less than or equal to 0. So what kind of points does B have? It is 0, 0, S. So anyway, if I take inner product, lambda tilde dot 0 plus nu tilde dot 0, that will give you 0. So what you end up with is this assertion that mu of t is less than or equal to alpha for all t, no, sorry, is less than or equal to alpha star. So why so? Because what kind of points does it have? So B has the points 0, 0, S, right? So inner product with this will give you just mu S. And mu S is supposed to be less than or equal to 0. Oh, right. I forgot an alpha here. Yeah, my bad. So you also need an offset, right? Not only do you need a normal vector to define a hyperplane, you also need an offset. So if this is the offset, this is what you have. Mu S is less than or equal to alpha for all S in B. So let me rewrite this. So that means mu of t is less than or equal to alpha. So by the way, this is different from the alpha star. So mu of t is less than or equal to alpha for all t such that t is strictly less than alpha star. So why so? Because if t is less than alpha star, then 0 vec t belongs to B. And when I take inner product with this lambda tilde vec, nu tilde vec with mu, then inner product is 0 dot. So you can do it just component wise. So this inner product is 0, this inner product is 0, this inner product is mu times t, and that must be less than or equal to alpha. And here, since 0, 0 t belongs to B, then t is less than alpha star. So that's exactly the interpretation you get. So there is some, there exists lambda tilde vec belongs to Rm, nu tilde vec in Rp, and mu in R, such that this holds. So that was for part B. Now for A, what do we conclude? For A, we have lambda tilde vec transpose U, or inner product, whichever way you want to think of it, transpose V plus mu times T is bigger than equal to alpha for u v t in A. I mean, this is just rewriting what inner product means and what this half, like belonging to this positive half space, what does that mean? So from here, I want to claim. So claim is, first of all, lambda tilde vec is bigger than equal to 0. And second of all, mu is also bigger than equal to 0. So proof of claim. All right. So if mu is strictly less than 0, then what happens? Uh, Yeah, right. So here I'm saying for all t such that t is strictly less than alpha star. So I can choose t to be as small as I want. It can be very, very negative, right? So if mu is strictly less than 0 and t is a very small number in the sense that it may have very high magnitude, but its sign is very negative. So in that case, mu times t will have a very big magnitude and also be positive, right? Mu is negative, t is negative, product is positive. So at some point, it will exceed this alpha. So it will contradict this. So if mu is strictly less than 0, then choose t less than alpha star with mod t bigger than alpha over mod mu. Then what we have is mu t is in fact equal to mod mu times mod t is bigger than alpha, contradiction. So this implies that you will always have the mu is bigger than equal to 0. So now what about lambda tilde vec? So why should that be bigger than equal to 0? All right. So if one of the when I say lambda tilde vec is bigger than equal to 0, it means coordinate wise, entry wise, it is bigger than equal to 0. All the entries are actually non-negative. So let's assume one of these entries is strictly negative. That means it corresponds to one of these i's, right? From 1 to m. The lambda tilde has lambda 1 tilde, lambda 2 tilde up to lambda m tilde. That corresponds to the gi's. So in that case, what do we have? Yeah. Right. So in that case, what you do is yeah, I mean, it will be a very similar argument. You can prove that this actually can be sent to minus infinity if lambda tilde is strictly less than 0 for some 0. But yeah, let's complete this argument. So if so without loss of generality, just let's say if lambda 1 tilde is strictly less than 0, then I want to choose, I want to be able to choose a u. Okay, right, yeah. So now we just have to stare at this definition. First of all, if something like ui vj t belongs to A, then if I take anything bigger than ui, it should also belong to A, right? I fix vj and t because then gix for that particular x will also satisfy this inequality. And here it is just demanding there exists some x such that these inequalities are satisfied. So I can in fact choose ui to be very, very positive, right? Right. So if lambda 1 tilde bigger than is strictly less than 0, so we may choose u1 to be as large as we want. So u1 very bigger than 0, which means lambda 1 tilde times u1 will be less than 0. But then and fix the other terms, like fix the other terms and just change u1, let's say. So in that case, this will actually tend to minus infinity, or in other words, it can be made as small as possible, but it will contradict this inequality. And we are keeping fixed. V and t we are keeping fixed. Just to rephrase what I said, if u v t belong to A, then anything bigger than u can be put here, independent of what v and t are. Like if u1 is bigger than u2, in the sense all the coordinate wise it is bigger, then I definitely have. So if this is true and u2 vt belongs to A, then u1 vt also belongs to A. That is exactly what I said in this, because u1 vt belongs to A. What does that mean? That there is some x in the domain, so that gi of x is less than or equal to ui, and so on. Perhaps this is bad notation because there is a ui here. maybe I just say W here. So if W is bigger than U, then this is true. Because this means Gi of x is less than equal to Ui, which is less than equal to Wi. So in fact, there is some x such that Gix is less than equal to Wi and Hjx equals Vj and f naught x is less than equal to T. So we have this sort of arrangement here. Okay. So that is why we must have lambda tilde for each of the entries of lambda tilde must be non-negative. So essentially it is starting to look like some sort of feasibility condition. And on nu tilde, we don't have any conditions. All right. Now, so mu, it is positive and we have mu t is less than or equal to alpha for all t strictly less than alpha star. So in particular, by taking supremum, I will have mu of alpha star is in fact less than or equal to alpha by taking supremum over all t, and since mu is positive or non-negative. So, and another thing, similarly, so from the other inequality, what we have is summation I equals 1 to m lambda I tilde fi of x plus nu tilde vec ax minus b. By the way, this is all the affine conditions, affine equality constraints. Remember, all the HIs are in fact of this form. So I'll just pull them together and write it like this, ax minus b. So we, in fact, for the feasible set, we have ax is equal to b. And then plus mu times f naught of x is bigger than equal to alpha. And from this inequality, what do we have? This is bigger than equal to mu of alpha star. Okay, so now we have two cases. This, because this left hand side is actually looking very suspiciously similar to the Lagrangian dual, right? All I have to do is, so in the Lagrangian dual, this component of mu is not there in front of f naught. You just have the objective function, just f naught. So I want to divide by mu throughout. I know that mu is non-negative, so if I divide, the inequality will not be reversed. Only issue is whether I can divide or not. So that I'll divide into two cases. Mu is strictly bigger than 0, in which case I can actually divide both sides and have this inequality. Summation I equals 1 to m lambda I tilde divided by mu fi x plus 1 over mu. So this vector transpose ax minus b plus f naught x is bigger than equal to alpha. Sorry, alpha star. Now this is nothing but, so just by definition, this is Lx, the Lagrangian, lambda tilde vec divided by mu, nu tilde vec divided by mu. And this is bigger than equal to alpha star. And how was f defined? F was defined, you take infimum over all x belonging to the domain. So this implies f of lambda tilde over mu, nu tilde over mu is bigger than equal to alpha star. So what exactly is this telling us? First of all, this vector is dual feasible. So remember, what was the dual problem? You want to maximize this function f of lambda tilde nu tilde, where lambda tilde vec is bigger than equal to 0 and nu tilde is free. But this we have already established, right? That was important. So it was not just some side story that we were trying to explore. It was actually important for the proof. So this is dual feasible. And we have f evaluated there is bigger than equal to alpha star. So maximum of f must be bigger than equal to alpha star. So maximum, the optimal value of f lambda vec nu tilde, or I should say, let me just say, so optimal solution to the dual problem, so which we have been denoting by beta star, which is maximum value of f lambda vec nu vec, where lambda vec, so subject to lambda vec bigger than equal to 0, and nu vec is, so belongs to Rp. But so optimal solution is beta star. So what does this tell us? That beta star is bigger than equal to alpha star. But by weak duality, we have beta star is less than equal to alpha star. So in conclusion, we have beta star equals to alpha star. That means the optimal duality gap is in fact equal to 0. Or in fact, this is going to be, we're going to see strong duality. The maximum of the dual is in fact equal to the minimum of the primal. And not only that, it in fact tells you that this exact inequality must be an equality. So in fact, f of lambda tilde vec by mu vec tilde over mu is in fact equal to alpha star. So this is a dual optimal solution. Remember, when we are talking about Slater's theorem, we are talking about two parts. One was it shows that strong duality holds. The other part asserts that the dual optimum is in fact achieved, and we have found the points where it is achieved by finding what mu, lambda, and lambda vec and nu vec are. All right. So this was case where mu is strictly bigger than 0. So then you must be wondering why these Slater's conditions? We have not used Slater's conditions so far, right? I mean, this part just works for any type of condition as long as the problem is a convex optimization problem. Here, the two cases mu bigger than 0, it is actually very much related to how we define convex functions. We use convex sets, that's for sure, that epigraph is convex and so on. But we have a very specialized direction which we want to avoid when we talk about epigraphs. That is this direction, that is the vertical direction. In the general theory of convex sets, you don't care. But when you're talking about functions and graphs of functions and so on, there is a distinguished direction known as the vertical direction. And when we use separating hyperplane theorem and so on, we want to avoid this because, I mean, it's not going to give something like interpretable. So case 2, when mu is equal to 0, what exactly is it telling you? So we have a separating hyperplane where mu is equal to 0. Then it is telling you exactly that you have a vertical hyperplane. So mu is 0, mu is supposed to point in this direction. So that part is 0. So all of these are in fact, so in fact, everything of this form 0, 0, s, inner product with lambda tilde vec, nu tilde vec 0, because mu is 0. The inner product is always going to be 0, right? So all of these points are orthogonal. 0, 0, s are going to be orthogonal. So they will lie on the hyperplane, right? So 0, 0, s, all these points of the form will lie on the hyperplane. So in fact, this will be completely vertical. So Slater's conditions will ensure that mu equals 0 cannot hold. So not possible due to Slater's condition. So again, remember, when we are talking about describing the epigraph of convex functions or describing convex functions as arbitrary supremum of affine functions, the problem with vertical hyperplanes was that there you cannot really talk about supremum or infimum of that affine function, because the supremum is infinity, the infimum is minus infinity. So it is not really gelling well with the way we want to describe things. Now, if I define mu to be 0, then B is completely contained inside this hyperplane. So in fact, it is something like this. You have, this is your A, then B is somewhere here. B is, so this is, let's say, the separating hyperplane. B is somewhere lying in here. So in fact, it will correspond to certain conditions like alpha star is minus infinity or something of that nature, where anyway strong duality holds. But because weak duality will imply beta star less than equal to alpha star. So if alpha star is minus infinity, then beta star must be minus infinity. And we are trying to avoid that condition. Okay, so let's prove that mu equals 0 is not possible. So what does mu equals 0 really mean? So we look at this condition right here. So mu equals 0 means the objective function has disappeared from the picture. So what you are left with is I equals 1 to m lambda I tilde fi of x plus nu tilde t ax minus b. And this is bigger than equal to 0, right? So stare at this again. This part is 0 because mu is 0. This part is 0. So you have lambda I tilde summation fix plus this nu I tilde, let's say aix minus bi. So these are all bigger than equal to 0. All right. So now by Slater's conditions, there exists x tilde vec such that fi x tilde is strictly less than 0 and ax tilde vec is equal to b. But what does that mean? But we have shown that lambda I tilde is bigger than or equal to 0, right? So the product, if any of these is actually strictly bigger than 0, then the product is going to be strictly less than 0. And anyway, this part plays no role for that x tilde. So that would mean that this inequality is not satisfied, right? So this implies, in fact, lambda I tilde equals 0 for all I between 1 and m. Because, again, repeating this argument, that if this is non-zero, because it is non-negative, it must be strictly bigger than 0. And for that, and plugging in x equals x tilde, we have fi x tilde is strictly less than 0. So that product is something which is strictly less than 0. So in that case, the summation is going to be strictly less than 0, which is contradicting this inequality. So our conclusion is that all of these are in fact going to be 0. So what we are left with is nu I vec tilde ax minus b is bigger than or equal to 0. So here, and where is x? So that's why the distinction between the domain and like what is omega and the feasible set is important. So omega and d are different. So that is to remember, this is the feasible set. This is the domain. So here when we are talking about this inequality, when we talked about A, remember, x is in the domain. X is belongs to omega, not D, where D is that feasible set or decision space, as we have been saying. So here what will happen is x will be free. So without loss of generality, let's assume that A is full rank. Otherwise, we have uh, either the system of equations ax equals b is inconsistent. In that case, the feasible set will be empty, but that's not what we're really looking at. So if it is non-empty, that means ax equals b does have a solution. I can always remove the redundant equations and assume A is full rank. So without loss of generality, assume A is full rank. So we could have done it in the very beginning. All right, so now x actually lie, you can check, so x belongs to interior of omega, and without loss of generality, you can in fact assume omega interior has dimension m plus p plus 1. So it's an element of, or omega is sitting inside R to the m plus p plus 1. And that's because you're able to perturb this mu I ui on both sides. So x also you're able to move along in omega. Okay. So with this, what do we have? We have nu tilde vec transpose ax minus b is bigger than or equal to 0 for all x in a ball in Rm plus p plus 1. Did I say no, that's wrong. That's wrong. This is not m plus p plus 1. That's the range space. This is in fact has dimension n. X belongs to Rn. Omega is a subset of Rn. The range set, including all this Fix and also on, will be in Rm plus p plus 1. But this has dimension n. Let me erase this. Okay. So now what does that mean? That means if I'm looking at this, Ax is bigger than or equal to this. This is defining a hyperplane, right? And it is saying that every point in this unit ball is on one side. That is never possible. If I have a ball and I'm taking a hyperplane which passes through this ball, then like there has to be two sides to the ball. You cannot have everything on one side. And remember, when I take x to be some x tilde, some element in the feasible set, then this is actually equal to 0. Yeah. So, and this is a fixed number because b and nu are fixed. So all I'm saying is if I choose any x, nu tilde ax is always bigger than or equal to this number. So that is not going to be feasible. If I choose, for example, the opposite direction, like minus x, for example. Let's say I have this, I choose the opposite direction, this sign has to change, right? So what that would imply is that nu tilde transpose A is in fact equal to the 0 vector. Only then you can have such type of equality or inequality depending on whether this is positive or negative. If we choose this to be 0, then this is 0, so it's essentially implying that this part is negative. Okay, so this implies A transpose nu tilde is in fact equal to 0. This implies A does not have full rank. Okay. So, but we started with the assumption that A has full rank. So that means such a nu tilde cannot exist unless nu tilde is 0. So not only lambda I tildes are 0, also the nu tildes are 0. And then it is contradicting the fact that, so this implies, okay. So instead of looking at it in the contradiction point of view, let's just say this implies nu tilde vec is in fact equal to the 0 vector since A is a full rank. But that means mu is equal to 0, and we had shown that this is equal to 0 and this is equal to 0. That means this normal vector is a 0 vector, and by our choice this is a non-zero vector in the separating hyperplane theorem. Perhaps I didn't mention it, but it should have been obvious. This is always going to be a non-zero vector. Otherwise it will give you all of Rn, right? If you chose a 0 vector there, either it is empty or it is all of Rn. Okay, so contradiction will be arrived here. So case 2 is impossible. So mu equals 0 is impossible. So you don't have any vertical things. Like in the separating hyperplane is not vertical. And if you have something not vertical, then it must hit this A at some finite value. And that is exactly the point you're looking for. All right. So another, like this is like one of the highlights of this course, I would say. So we are almost nearing the end. And like I had mentioned last time, the last class will be this Thursday. Next week will not meet next week, so that hopefully that will give you some more time to prepare for your exams. And next class, in fact, I will give you a summary of the whole course so that you have a complete like big picture view of the whole course. What things are important? It's like a cheat sheet. Like what are 10 things I wish I take away from this class? So that kind of lecture. But I had promised also last time that I will give you an example of a non-convex optimization problem where strong duality holds, right? Here, like Slater's conditions and everything, we are talking about a convex optimization problem, and there we concluded, okay, if these conditions are satisfied, then strong duality holds. Yeah, but we want to see a non-convex optimization problem with strong duality. And that is helpful, right? Because we know that if this satisfies strong duality, to find the optimal value, what I can do is actually look at the dual problem, which is actually a convex optimization problem. And there we have all these techniques, like for example, maybe you can use gradient descent and so on, because it's a convex function, you'll have unique maxima. And so life becomes much simpler. And then by strong duality, you have whatever maximal value you get, that is the same maximal value for your original non-convex optimization problem. So we'll see an example. For that, we'll have to take a long detour. We have an hour before the class ends. So in order to even talk about this example, we'll have to take a long detour. So, but anyway, let me mention this example. So minimize this thing, x dot ax plus 2b dot x subject to, so on the unit ball, norm of x, so Euclidean norm is less than equal to 1. So this is Euclidean norm. So on the unit ball, you want to minimize this. And A is a symmetric matrix. So A is a symmetric matrix, n by n matrix in M and R. I'm not assuming positive semi-definite or anything of that nature. And B is some vector in Rn, and X. So these all X are in Rn. All right, so this is the problem I want to look at. Actually, we have seen this sort of problem when A was positive semi-definite. In fact, it was positive definite. When A was positive definite, we have actually solved this problem more explicitly by using least squares and using the fact that for a positive definite matrix, x dot ax is always bigger than equal to 0. and so on. We just use, I believe, A inverse B or minus A inverse B, something like that. So a couple of lectures ago, we had in fact solved this problem. But this, so if A is positive semi-definite, this objective function f naught of x equals x dot ax is convex, and the converse is also true. Something of this form is convex if and only if in fact A is positive semi-definite. So how do you see that? You just compute the Hessian, and when you have the Hessian, what you notice is the Hessian will turn out to be exactly A, or some multiple of A, um, a positive multiple of A, and then it is quite clear that since the Hessian is positive semi-definite, it must be convex. Like these are some conditions for convex functions we have already seen. So checking that this is convex is easy. So minimizing this should not be super hard. Like there has to be a unique minimum. Either it goes to minus infinity or there is a unique minimum. And for the positive definite case, we actually found an exact expression. All right. But if it is not positive semi-definite, we know that this is not convex. If A is not positive semi-definite, then f naught is not convex. All right, but even though it is not convex, there is a way to in fact solve this minimization problem. And just like the simplex method was a very special case, right? It was a linear. So if you forget about this term, then it was essentially something about you have a convex set on which you are trying to optimize this sort of function. So this is kind of upping the ante. Now you have introduced a quadratic term. So in this case, you can in fact, or at least for this type of problem, you can in fact do it in a more systematic manner. Instead of having an algorithm, you can in fact give a more closed form solutions or closed form answers. So our detour will be about that. And then at the end, we'll reach a solution, and then we'll talk about how we'll look at the dual of this function. And then you strong and notice that in fact, this satisfies the strong duality property. We have a non-convex objective function, but our feasible set is convex, but here strong duality holds. So hopefully that will be our end result, that strong duality holds. So here we are going to take a detour in linear algebra. So most of the concepts we'll cover today you have already seen, but maybe in a scattered manner. Even in this course, you have seen this theme, but in a scattered manner. So we'll try to kind of make it more systematic. So we'll talk about something known as generalized inverse and pseudo inverses of a matrix. Generalized inverses and pseudo inverses. Pseudo inverses, otherwise known as Moore-Penrose inverses. Okay. All right. So first, just as a reminder definition, we have a square matrix A, M and R is invertible, or is said to be invertible, if there is some matrix B such that AB equals B equals identity. Is said to be invertible if there exists a square matrix B in M and R such that AB is equal to BA is equal to IN, the identity in M and R. So this is something which is very familiar, and we have many conditions to check for invertibility. For example, if A is a square matrix and has full rank, then it is invertible. Or A has non-zero determinant, and in a basic linear algebra course, you see multiple like null space is empty and so on. Or zero, so it's not empty, but null space is just zero dimensional. Okay. And a quick application of this, and which something which we have used, especially in the simplex method, because linearity was just floating around everywhere. The equation ax equals b has a unique solution. So if we have a linear system of equations and we wrote it in this matrix form, and we noted that A is invertible, then the unique solution here is given by just A inverse B. So this is how life becomes much, much simpler if we have A is invertible. Now the question is how to solve, or how to do some sort of generalized inverse operation, how to solve Ax equals B for general matrices A, not just invertible, not even square, meaning neither invertibility nor squareness is assumed. So neither invertibility nor squareness is assumed. So for example, so there are two questions one could be interested in. So if our goal is to solve Ax equals B, first of all, if this equation is consistent, meaning you're getting a feasible set, then we want x star with minimal Euclidean norm. This is again a convex optimization problem. What are you saying exactly? Minimize x dot x subject to Ax equals B. This is a convex function. Identity is a positive semi-definite matrix. It's a convex function. And your feasible set is a polyhedron. All right. So this is one type of question. You want to solve Ax equals B, then, and you want to find amongst all these solutions you have, either you have a unique solution if A is invertible, or typically what you will have is a linear class of solutions. You have a particular solution and then you solve X equals 0. Then you perturb any particular solution by a solution to the homogeneous equation, and then you get every other solution. So it is an affine space. We have seen this description of affine spaces way back in the beginning when we were talking about convex geometry. So here we want to find X with minimal Euclidean norm, meaning it is the offset. So this is the affine space, this is the center, this is the origin. You want to find this X star, that is the offset, by solving this problem. So this is one motivation. Again, this is an optimization problem. Second is, let's say this is not consistent. If Ax equals B is not consistent, we want to find X which minimizes the distance of Ax and B, which minimizes norm of Ax minus B, L2 norm, Euclidean norm. Or in other words, so Ax is essentially the range. So this is the range. If I vary X all over Rn, so this is range of A. So what might happen, B may not be in the range of A, right? Range of A is an affine subspace. In fact, it's a linear subspace. So range of A is a linear subspace of R M. Yeah. Because A, let's say A belongs to M and R. So it is acting on vectors in Rn. It is sending Rn to Rm. So range of A is a linear subspace of Rm, and B is a vector in Rm. So this is another like kind of problem you might be interested in. If X equals B is not consistent, but you want to find the best possible value of X such that Ax like matches up with B. So here Ax will be a linear subspace like this. The origin is here, B is outside, and you want to find whatever X is approximating B. So intuitively, it will be like the orthogonal projection from B to this range of A. Intuitively, you can believe that, okay, if I want to identify some point in the range of A with B, it better be this point. It is the closest one to B. So these are two types of problems. And in fact, the second problem is the one you solve in linear regression. Okay. So essentially, these are the slope vectors. So essentially, you have beta 0, beta 1. This is the vector. You want to find such, and these are the data. These are the value of the predictor variables. B is the value of the predicted variables, so the response variables. And ideally, you want AX equals B. So whenever you plug in so X also looks like a variable. In fact, it is all those slope parameters, beta 0, beta 1, beta n. So yeah, ideally you want it to be a perfect match or perfect fitting, but you don't get it. So you say, okay, like what is the closest fitting I can get? So that is the like what is the parameter X I can choose so that I get closest fitting with the training data. So these problems are in fact that are very useful and like familiar to you. Just like we phrased this as an optimization problem, let's rephrase this. So essentially, what do we want to do? We want to minimize AX minus B, AX minus B, subject to X belongs to Rn. So no constraints are there. Now what does this look like? If I expand this out, it starts looking very familiar. This is A transpose AX, then minus 2 times A transpose B X, plus you have this B dot B term. It's anyway a fixed constant. It doesn't matter in the minimization or maximization problem. It does not matter. Now this is a positive semi-definite matrix. A may not be invertible. So positive semi-definite matrix. So it's a convex function. So minimum will exist in all of Rn. And in fact, even if it is not 0, and this function is always bigger than or equal to 0, so the minimum will exist because it's a convex function. So based on this interpretation, it looks like we need a process where we talk about invertibility of non-invertible matrices. So that is where we'll get. So using these two problems as motivation. Again, like, so essentially it is wrapping back to our course on optimization. We're trying to optimize certain function on a feasible set. All right. So want to solve Ax equals B in both these senses. There are in two senses in which we wanted to solve. One was if there is a solution, find the smallest one. And if there is no solution, find the closest possible solution. So want to solve without the assumption of full column rank. Yeah. Another thing is if there is full column rank, then this will be in fact positive definite. This will be invertible. And the solution you'll get for this is A transpose A inverse A transpose B, because this vector is A transpose. And we have already talked about optimizing this function in a previous class where we had something like x dot ax plus 2b dot x. So essentially it turned out to be A inverse B. So here A is replaced by A transpose A and B has been replaced by A transpose B. So the solution, in fact, if A is full column rank, then A transpose A inverse A transpose B. So in linear regression, in multiple linear regression, when you see in your statistics course, it will essentially be, these will be called normal equations. A transpose AX is equal to A transpose B. Then if this is invertible, then you can move it and get a unique solution. But this equation will hold, it doesn't matter whether A is full rank or not. These normal equations will always hold. And here X is like the slope parameters, slope and intercept parameters. All right. Anyway, so this is the body of ideas. So when you see this in statistics, maybe 3, this will start looking very familiar. Anyway, so the main point is we want to do this without the assumption of full column rank. All right. So one thing to notice is if we are solving A transpose AX equals A transpose B, which is based on differentiating this with respect to X and equating it to 0, because if this is a minimal value, then the derivative must be 0. So that's exactly where you get this normal equation. You take the gradient and set it equal to 0. So what do we notice? So some sort of remark. If A is a full column rank, so that A transpose A inverse is well defined, A transpose A inverse A transpose is sort of a pseudo inverse. of A. So why so? Typically, to solve the equation Ax equals B, you'd write X equals A inverse B, right? But here, instead of writing A inverse B, you're writing something like A transpose A inverse A transpose B. So this is kind of playing the role of A inverse when in this problem it is inconsistent, when you don't have a full solution to this. So this is like draw analogies. So this is looking like something like a pseudo inverse. And optimal solution is pseudo inverse acting on B, right? So generally the solution will be inverse acting on B, but here optimal solution is pseudo inverse acting on B. The second part to remember is if I multiply A here, this is what is known as a projection matrix. We'll talk about a little bit from now. This is just to get you motivation. Projection meaning, first of all, you can see that this is a symmetric matrix, right? If I take transpose, the A transpose will become an A. This A will go and become an A transpose. This is symmetric, so it will stay put. So this is a symmetric matrix. And if you multiply it twice, meaning if you do this, so first of all, this part will cancel off here. You will end up with, so if you multiply it twice, you get back the same matrix. So this is in fact symmetric and idempotent, meaning the square is itself. That is precisely the definition of a projection matrix. It's a square matrix which is symmetric. Of course, it is symmetric, hence it's a square matrix, so I don't have to say it twice. Yeah, it's a symmetric matrix and it is an idempotent. So this is the algebraic way of looking at projection matrices. The geometric way is to see that a projection P, so which satisfies P square equals P and P transpose equals P. Then if you look at say V equals range of P, then P of V, so P of X equals X for X in V. So essentially, if you're already projected onto the whatever range of this projection matrix, then you stay put, you stay invariant. It's like you have the subspace and the projection matrix essentially takes any vector and projects it here. But if you're already here, there's nothing to project really. It's already there in your subspace. So you stay put. But if you have something perpendicular to this space, so X belongs to V perp implies Px is equal to 0. Then when you project, essentially it just squishes down to something which is like a point. So that is 0. So that is the geometric interpretation of these projection matrices. So there is a one-to-one correspondence between linear subspaces of this, let's say, inner product space and projection matrices. All right, so this already is indicating you that these two concepts are going to be crucial in our description. Actually, it just squishes down to something which is like a point. So that is 0. So that is the geometric interpretation of these projection matrices. So there is a one-to-one correspondence between linear subspaces of this, let's say, inner product space and projection matrices. All right, so this already is indicating you that these two concepts are going to be crucial in our description. All right, so let's, with all this intuition in mind, let's go through a few definitions. So generalized inverse. So A belongs to an M by N matrix, MNR. So then G in MNR. So it is reversed. N and M are reversed. So if MA is an M by N matrix, G is an N by M matrix. So then is said to be a generalized inverse of A. A generalized inverse of A if AGA is equal to A. If this is true, then G is said to be a generalized inverse. And what is the connection between, let's say A is already invertible, then the generalized inverse, there is a unique generalized inverse, And that is precisely the inverse of A. For an invertible square matrix, there exists a unique generalized inverse. So in no part of the definition is it made apparent, and in fact, it is not even true that generalized inverses are unique. Although you can completely characterize how all generalized inverses look like. So G is just equal to A inverse. Okay. Yeah, so one advantage of having a generalized inverse is clear. Like, let's say you found a generalized inverse and you want to solve Ax equals B. If I multiply Ag to this, what do I get? Agax is equal to Gab. Sorry. Yeah, so this is, which is in fact equal to B, right? So Agax, let's say there is a generalized inverse of that nature, and I want to solve Ax equals B. Then I have Agax. First of all, since Ax equals B, I must have Agb. But at the same time, by the definition of generalized inverse, I know this is equal to Ax. So it's equal to B. So what I have is Agb is equal to B. So knowing the generalized inverse gives me a recipe to solve this. This implies X star equals Gb is a solution to my equation. Just as the inverse gave you an immediate solution, that A inverse B is the solution, here if you have a generalized inverse, then G of B is also giving you a solution to this equation right here. And of course, as you change your choices of G, then your solutions also change. There might be infinitely many solutions. Yeah. So now the question is, how do I find one such G? And we'll not spend time on finding such a G or even proving existence. So we have not even proved that every matrix A has a like there is some generalized inverse. Forget about uniqueness, which is not even true. Existence also has not been proved. We will not prove it because we'll talk about a special case of generalized inverses known as pseudo inverses, and we'll show that they exist. So clearly, every pseudo inverse is a generalized inverse, and if pseudo inverses exist, then generalized inverses must exist. So that's why we'll not try to double our work. So just keep in mind that they always exist. That's all. So here's the theorem. Okay. So remember, our motivating theme is to try to solve linear equations in two different senses. One is if it is consistent, then try to find the smallest solution, like in the Euclidean norm. If it is not consistent, find the solution which is closest. Okay. So let's say you have Ax equals B, which means B is in the column space of A. So that is, the system is consistent. All right. Now let G be a generalized inverse of A. Yeah, this is just a rehash of what I just said. That is, AGA equals A, then GB is a particular solution to this system. This is exactly the remark I made. All right. Now, another thing to note is if AGA equals A, this implies AG is equal to AG. I'm just multiplying G on both sides. So this implies AG, just rewriting, square is AG, or AG is in fact an idempotent matrix. I'm not saying symmetric or anything like that. So even for idempotent matrices, you can think of them as projections, but an angled projection. like you're projecting in this angle. The orthogonal projections would mean you just directly drop a perpendicular, but you have some angle theta here, and based on that, you're projecting. So idempotent matrices also, you can think of it that way. Okay. So with this in mind, all of these theorems, if you understand linear algebra really well, should be quite intuitive. So next result is that if I have an m by n matrix A with generalized inverse G, in NMR, n by n m matrix, then AG belongs to R, m by m is an idempotent matrix. Okay, an encapsulation of the remark we just made. And one thing we have to note is AG and A must have the same column space. For example, G, I mean, it's not that this is a defining property that AG is an idempotent matrix. For example, if I choose G equals 0, then A times 0 is also idempotent because it is a 0 matrix. But here, AG is very close, it's an idempotent matrix which is very closely related to A. In fact, it is some sort of projection onto the column space of A. So AG is projecting, not orthogonally generally, but projecting onto the column space of A. Okay. And similarly, GA is an idempotent matrix projecting onto the row space. Onto the row space of A. You just prove GS. All right, so let's dwell on this a little bit. So first of all, the column space of AG is contained in the column space of A is clear. You multiply anything on the right, the column space is not going to be changed. But so what I'm saying is column space of A is contained in, column space of AG is contained in column space of A is clear. But at the same time, what is A? A is nothing but AG times A, right? So that would mean the opposite direction is also true, that the column space of A is contained in the column space of AG. So which means they both have the same range. All right. Okay. So next, so like I said, so this was just giving a brief idea of what generalized inverses look like. So next we'll talk about a special form of generalized inverses known as pseudo inverses. So generalized inverses are also known as Penrose inverses, according to the based on the name of the mathematical physicist Roger Penrose. And this is known as Moore-Penrose inverse because Moore is the person who actually talked about this special form. So pseudo inverses, also known as Moore-Penrose inverse. Okay. So here we'll have some extra properties, not just AG A equals A, but we'll have certain additional properties which will guarantee uniqueness in some sense of this. So let A be a m by n matrix and B be a n by n m matrix. Then B is said to be a pseudo inverse of A pseudo inverse of A if it satisfies the following condition. If it satisfies, first condition is ABA is equal to A, which means B is a generalized inverse or a Penrose inverse of A. And we want some sort of symmetry of this property, meaning if A is a pseudo inverse of B, then B is a pseudo inverse of A. And in fact, all of these properties you can check, they're absolutely symmetric about A and B. BAB is equal to B. A is a generalized A is a generalized inverse of B. 3 is that AB is symmetric. AB transpose is AB, that is AB is symmetric. And the fourth point is that BA is symmetric. So all of these conditions kind of, first of all, like pseudo inverse of pseudo inverse again gives you back the original thing, A. So that's one good thing, which is very similar to what happens with inverses. A inverse inverse is again A. And the other thing is that this is not only B exists, you can we'll show that very briefly. In fact, it will be a quick proof, but yeah, it exists and is unique. So this also kind of guarantees some sort of uniqueness, and there is a good interpretation to this uniqueness. So I mean, uniqueness typically means something is very special, right? Like there's just one of it. So so yeah, I mean, it gives that defining special property for this pseudo inverse. All right, so proof. Okay, I mean, there's no theorem. The theorem is, so every A in MMNR has a unique pseudo inverse. So here, when I say has a unique pseudo inverse, I mean two things. First of all, it has a pseudo inverse and it is unique. So it both exists and is unique. So first of all, how do we prove uniqueness? This is the easy part. So let's say, and typically once you know that it is unique, it is denoted by a dagger. So A, there's like a dagger, something like this. All right, so let's say there is some other B which satisfies all these four conditions. Assume B and C satisfy the four conditions. Now consider this new matrix H equals AB minus AC. So clearly this is symmetric, right? Because AB is symmetric, AC is symmetric by condition number 3. So AB and AC are both symmetric, so this H is symmetric. So now what about H squared? So H squared I can write as AB minus AC, A times B minus C. Now I'll take A common. Now this part I can write as ABA minus ACA times B minus C. So this A I have absorbed here. But then looking at property 1, I have ABA is A, and then ACA, because B and C are both satisfying these four conditions. So I have this. So I have a symmetric matrix whose square is 0. Note that if I have a symmetric matrix, its square is positive semi-definite. And the only positive semi-definite matrix which is 0, that means H must already be 0 if H squared is 0. So it's essentially, think of it as you have eigenvalues by the spectral theorem which we have learned in linear algebra. H is symmetric, it has all real eigenvalues. Then when I square, the eigenvalues of the square are lambda 1 squared, lambda 2 squared, and so on. And that is equal to 0. That means individual eigenvalues are 0, which means originally the matrix must have already been 0. So this implies H equals 0, which means AB is equal to AC. All right. So once we have this, I'm going to write B, first of all, is nothing but BAB. That's condition number 2. Now BAB is BAC. Oh yeah, and by the way, similarly, if you, instead of looking at AB minus AC, we could have written looked at BA minus CA, and eventually would have concluded again BA is equal to CA. So similarly, BA equals CA. So how, so far which conditions have we used? First of all, we have used this and this because we want to go both ways, right? AB minus AC and also BA minus CA. And then we have used condition 1 also. Condition 2 is the only one remaining, which is something which we'll use here. So this is condition 2. 2 implies B is equal to BAB. But since AB is equal to AC, we have BAC, but then BA is equal to CA. That is condition 4. But again, going back to condition 2, I have this is equal to C, which implies B is equal to C. So I had two things satisfying all the four conditions, and I concluded that they must actually be equal. We denote the unique pseudo inverse, if it exists, by a dagger, like I said. So for existence, you need something known as the singular value decomposition. Perhaps you may have seen this, but the proof is again not that hard. So proof of SVD. So what is singular value decomposition? Essentially, any matrix A you can write in the form of U 0 0. So the R represents the rank of A. So rank of A and V transpose. So these are orthogonal matrices. And what is sigma R? So sigma R consists of singular values of A. In other words, which is equivalent to eigenvalues, or square root of eigenvalues of A transpose A. So this is the definition. This is precisely the definition. So singular values of A are, you look at the positive semi-definite matrix A transpose. So all the eigenvalues are positive. You take square root. Those are the singular values. So clearly, if I'm writing, and these are orthogonal matrices, so the rank will not change. So I'm essentially converting A to some sort of diagonal matrix, and all the diagonal entries are essentially square root of eigenvalues of A transpose A. So this can always be done. So this is singular value decomposition. And if this is M by N, you can imagine this is orthogonal matrix in M by M. This is N by N. Okay. And the proof, you can just give a proof by words in some sense. First of all, since A transpose A is symmetric, you have all these eigenvalues. Sigma I squared Vi. So sigma I is ith singular value. Sigma I squareds are the eigenvalues, and as I just defined, sigma I is the square root of this eigenvalue. So, and Vi are the corresponding eigenvectors corresponding to sigma I squared with norm 1. So these are norm 1 eigenvectors. I can scale it to have it norm 1. And then what I will do is define Ui in Rm. Note that these Vi's are in Rn, right? A is a matrix, M by N matrix. So it takes vectors in Rn to Rm. So Vi are in Rn. So define Ui in the following manner. A Vi over sigma I if sigma I is not equal to 0. So what about Ui? What is Ui dot Ui? It is nothing but A transpose A Vi dot Vi divided by sigma I squared. And by the fact that Vi is a norm 1 vector, this turns out to be 1. So Ui's are unit vectors in Rm. And also Ui Uj for distinct Ij again is equal to A transpose A Vi Vj divided by sigma I sigma j. So for I not equal to j, but we know that Vi Vj, if they are distinct, corresponding to distinct eigenvalues, then this must be equal to 0. And if they correspond to the same eigenvalue, I can always choose them to be normal to each other. So in essence, yeah, so you can always choose these UIs to be normal to each other. But what might happen is The range of A may not be the full space. In fact, typically that will not be the case. So in that case, extend or add an orthonormal basis of range of A perp, meaning the range may not be all of Rm, right? In fact, it could be just one vector, like one-dimensional space and so on. Then what you can do is you're free to choose. You take range of A perp, meaning the orthogonal space corresponding to range of A in Rm, and then you just pair them together, like pair those orthonormal vectors to whatever basis you got from the UIs. So in other words, you always have U1 through UM orthonormal basis of Rm, where initially Ui satisfy this. All right, and those are corresponding to all the non-zero eigenvalues. And then what is the change of variable? So if you have a linear transformation T from V to W, so any choice of a basis of V and W is giving you a matrix for T, right? So if I'm making change of basis here, so then essentially I get a change of coordinates, something like this, right? PAQ inverse. So here, what I'll do is choose Vi, I equals 1 to n, as basis for Rn, and Uj, j equals 1 through m, as basis for Rm. Then, so A from Rn to Rm has diagonal form in the above chosen basis for both domain and codomain vector space, in the above chosen basis. So when I'm talking about A as a matrix acting on Rn and Rm, the basis is the standard basis, like 1, 0, 0, 0, 1, 0, 0, and so on. But here I'm making a change of basis where I'm using Vi's, which are the eigenvectors of A transpose A, and then these Uj's are these vectors, AVI over sigma I, if sigma I not equal to 0, and if it is equal to 0, you just appropriately just pad in some extra orthonormal vectors. Yeah, and this is going to be in diagonal form because any vector x belongs to Rn is going to be of the form whatever, like alpha 1 v1 and all the way up to alpha n vn. Then when you apply x, what you're going to get is alpha 1 yeah, so alpha 1 av1 all the way up to alpha n avn. Now av1 is nothing but sigma 1 u1, so you're going to get alpha 1 sigma I ui and so on, and some of them will be 0, alpha k sigma k uk. Yeah, rest of them will be 0. Like I said, like but everything is in the span of the initial uis, right? So whatever you have padded in here as your orthonormal basis, that will just not appear in avi. And yeah, so this is in diagonal form. As you can see immediately that all it is just essentially like sigma I times ui if you chose this as your basis. Okay, so which shows that A is of the form u v transpose, this is v1 vn, so which is an orthogonal matrix un, and here you have these eigenvalues. Okay, so this is SVD, singular value decomposition. And once you have this, it is easy to see what a pseudo inverse should look like. Okay, so what's the formula of, so B, if we choose B to be equal to, let's see, so it has to go in the reverse direction. So still you have sigma R inverse 0, 0, 0 here. So I can invert because all of these correspond to the non-zero eigenvalues, in particular the non-zero singular values. Yeah. So I have V here and U transpose here. So let's check all those conditions. So we have all these conditions. AB A equals AB, AB equals B, and so on. So what's AB? First of all, V transpose V will give an identity of the appropriate dimensions. This is an orthogonal matrix, so forget about it. Then sigma R times this will again give an IR. So you'll end up with something like IR 0, 0 U transpose. This is clearly symmetric. And similarly, BA will give you V IR 0, 0 V transpose. So both of these are symmetric. Conditions 3 and 4 are satisfied. Now what about ABA? Then I have to multiply this. Then again, U transpose U will vanish. Then this product with this will give you sigma R. So ABA will be U IR 0, 0 V transpose. Oh, sorry, U transpose times. So that is AB. Then times A, which was U sigma R 0, 0, 0 V transpose. So this will give you an identity. Then this product will give you U sigma R 0, 0 V transpose, which is precisely A. And similarly, BAB is equal to B. So you can check. So in fact, this is giving you the unique pseudo inverse. Or in principle, you can think of it, of course, U will be equal to V. If A is a symmetric matrix, then U is going to be equal to V. A symmetric square matrix. So essentially the pseudo inverse, what it is telling you is that, okay, I mean, if I have some parts where my matrix is acting like 0, then I ignore that. In rest of it, it is invertible. So if I write A as so E0, that's the eigenspace corresponding to 0, plus some lambda 1 E1 plus lambda n En. Think of A as being symmetric. And this is the spectral theorem. You have the spectral projections corresponding to lambda 1, lambda 2, lambda n. So these are the eigenspaces. Then essentially A inverse, what it is doing is saying, okay, E0 is the one that is causing trouble in taking inverses, but I'll just replace it with E0 and rest I will do then inverse. So then when I multiply A inverse, so with a question mark, then these are all orthogonal. So in the product, you'll just multiply pointwise. Then I get this E0, E1. Okay, which is the identity. Yeah, typically, sorry, this is 0 times E0. Yeah, so the 0 is that corresponding eigenvalue, so 0 times E0. So you are not able to invert this, but if you do this, what you get is E1 plus E2 En plus 0. So essentially you get something like IR 0, 0, 0. Here this is the rank, right? Dimension of whatever else apart from the null space corresponds to the rank, right? So yeah, essentially inverting whichever does not correspond to the null space. So that is the idea of the pseudo inverse. All right. Now coming back to the problem that we were trying to solve, like the analogy or the motivation that we had was trying to solve for the slope parameters or the intercept parameters in multiple linear regression, right? And also there was another problem, the two problems that were motivating us. One was minimum norm solution to a consistent linear system, meaning it has feasible solutions, but you want to find the smallest such feasible solution. So here we will have a theorem which will tell us like why we had all this definition of a pseudo inverse. Was it just purely just some analogy, or was it actually very helpful? So let's say we have this and B is a vector in Rm. Then if Ax equals B is consistent, then X star equals A dagger B. This is the Moore-Penrose inverse or the pseudo inverse, is an exact solution with the smallest possible. So exact meaning it is not an approximate solution, it's an exact solution with the smallest possible norm. All right. So proof. So here, first thing that we have to notice is that anyway, for any inverse A dagger A is an idempotent for any generalized inverse, but this is in fact an orthogonal projection matrix. It is symmetric. Remember, one of the assumptions was BA is symmetric for B to be a pseudo inverse. So here, this will in fact be an orthogonal projection matrix. And so is A dagger. So this is an orthogonal projection onto the column space of A. For generalized inverses, we had said, okay, it is some projection, may not be orthogonal. It's a projection onto the column space of A, but here we can say A dagger is in fact an orthogonal projection. All right. So here we have AX equals B. So we look back at our geometric picture. So it is consistent. So you have this sort of, this is my affine hyperplane, not hyperplane, it's just an affine space, AX equals B. And I want to find the distance from the origin. So what do I really need to do? I want to just drop a perpendicular. So since this is a projection onto this space, like you take the offset, so onto this space. So let me redraw that diagram. So this is AX equals B. Now, if I have the origin, this is the equation AX equals 0. It is just translation. It is just translate. They're parallel to each other. So this plane or this affine set and this affine set are just parallel to each other. And it's a translation by B of this. So now, given any point here in this set AX equals B, we want to find the thing which is, we want to find the distance between these two hyperplanes and the normal vector. Okay. Now since this is the column space, this is projection onto the column space, and B is already in the column space because the system is consistent. So since AX equals B is consistent, meaning it has a solution, this implies B belongs to column space of A, which is equal to column space of the projection A dagger, right? That's exactly what we just saw here. So this implies, since it is in the column space of a projection, that means A dagger B must be equal to B. Its projection leaves its projection subspace invariant, right? B is in that subspace. So A dagger B is equal to B. So this implies A dagger B is a solution is to AX equals B. This I can just write A dagger B is equal to B. So this is my X. Now I have to show it has smallest norm, right? So for that, all I have to do is look at any vector X. Now I can split it up this into two parts. One is projecting onto this space, and then its orthogonal complement. Now, if I multiply, so since AX is B, then I have A dagger B. Okay, so X is a solution. So you start with some solution. I want to show that A dagger B is in fact the solution with smallest norm. So X equals, since X is a feasible solution, then AX equals B. So you have A dagger B here plus I minus this. Now this part is 0, right? Oh, right. No, my bad. My bad. So X, I can always split it up in this manner. One thing to note is inner product of these two quantities. So first of all, this is symmetric. So let me move it to the other side without having to write a transpose or anything like that. But this quantity is 0, right? Because A dagger is equal to A dagger A. That's the definition of a generalized inverse, and in particular pseudo inverses are generalized inverses. So this means this is 0. So what we have shown is A dagger B is perpendicular to this vector. Now if I have sum of two perpendicular vectors x1 plus x2 squared, this is the Pythagoras theorem, right? If x1 dot x2 is equal to 0. Using the bilinearity, you can easily prove, or you can think of this as Pythagoras theorem. You have two perpendicular vectors, then norm of this squared, which is x1 plus x2, is this norm squared plus this norm squared. So essentially, norm of x squared, L2 norm, the Euclidean norm, is nothing but A dagger B norm squared plus A dagger A x norm 2 squared. So since this is always a positive quantity, this is bigger than equal to, in fact, no, okay, yeah. So this is bigger than equal to this. So this shows that anytime you have a feasible solution, the Euclidean norm has to dominate this Euclidean norm. And this is already an exact solution. So this finishes the theorem, right? The theorem asserted that not only is A dagger B an exact solution, but it is the solution with the smallest possible norm. So we have solved that optimization problem. So this is actually optimization problem number 1. Okay. So now the second problem, multiple linear regression. So theorem. A minimizer for the problem minimize x over x in Rn for ax minus b. So here the system is not necessarily consistent. If it is consistent, then of course you have ax equals b, then you can go back to your previous problem and even minimize again within that domain. So that's why I have written a minimizer instead of saying the minimizer. Because for example, in the particular case where b is in fact a feasible solution, then the minimum possible thing is when ax equals b, and that can have infinitely many solutions, right? Okay, our minimizer for this is given by x star equals A dagger B. So here also the same solution. So somehow these problems are very, very related and almost look equivalent to each other. This is given by x equals A dagger B. Okay. Yeah, I mean, the geometric interpretation is also very similar. So essentially you have B somewhere here and you have AX. So this is AX and B may not lie in here. You want to project onto this. So projection onto Ax equals B is given by the matrix A dagger, right? So you have B here. Yeah, my bad. So this is actually a subspace. You want to project onto Ax equals 0. You want to find the distance of B to this. And you want to minimize that particular distance. So yeah, yeah, right. So I think I complicated it unnecessarily. So this is your plane. So 0 is in here. This is your plane given by Ax equals 0. And this is your vector B. And you want to find the value of x such that Ax is as close to B as possible. So essentially you want to drop a perpendicular like this. And that is the x star you're looking for. I mean, there might be infinitely many such, but that is one particular example that you're looking for. Yeah. And projection onto this is given by the matrix A dagger. We have already seen that. So my claim is AA dagger X must be equal to yeah, hence AA dagger B is the point on AX equals 0, which is closest to B. Or in other words, A dagger B is a point where AX minus B is minimized. Okay. All right, so that proves the theorem that A dagger B is a minimizer. Uh, then another point I want to think about is you have A transpose AX is equal to A transpose B. So this was the normal equations.
So how does that prove the theorem?
Yeah, so the theorem is
We
saying
need
that
we need a global solution, right? Like for Rn we need to check.
for Rn we need to check.
So this is the nearest point in Ax equal to 0.
Yeah. So the problem is here essentially you have this equation Ax equals 0. So you have this hyperplane and then you have this vector B. And I want to figure out like which is the closest point in Ax equals 0, which satisfies. So we want to minimize Ax minus B, right?
Oh yeah, right.
Right, like so Ax minus B is the translate, right? It is the translate of X0 which contains B. So essentially we are inverting the problem in some sense. So this
No, I think A dagger projects onto column space of A, right?
right.
So projection onto column space of A is given by A dagger.
Yeah.
Okay,
Okay.
then it solves the problem.
Yeah. So let me I think there is some scope for confusion here. Let me rephrase. Actually, this problem is no different from the first problem that we solved. So there we solved the way we interpreted it geometrically. Essentially, we have this equation Ax equals B, and that is defining an affine hyperplane or affine set, and we want to find the distance from the origin, right? So here it is similar. Here you have origin, and here you have the affine hyperplane Ax minus B, and you want to find X such that this is minimized. So you want to find X such that Ax minus, so X lying on this plane, on the plane Ax equals B, such that X is minimized. Oh, sorry, my bad.
I think like the sentence projection onto Ax equal to 0 should be replaced with a column space of A.
Yeah, so that I have already mentioned.
So now it's okay, I think. No.
Yeah, projection onto column space of A is given by this matrix.
So this point will
And
be nearest in the column space of A.
right. Right. Yeah, right. So here we're
Then we are
looking at
done.
the, yeah, right, exactly. Thank you. So A is a map from Rn to Rm. So here Ax, whatever, like you take all of Rn. So Ax, so range of A or column space of A is a subspace of Rm, right? And B is a subset of Rm. Yeah. So that's something, that's the distinction between the first and second problem. The first problem here, X was in Rn. And here we are actually looking at the same type of problem, but in Rm. Yeah, and we want to minimize this distance between the range of A and the vector B, right? Thank you. And once we have that, this A dagger B is in fact a point on the column space of A, which is closest to B, right? So yeah, forget about Ax equals 0. Yeah. So essentially this range, which is again an affine subset of Rm, and there we're using the same logic. All right. So here, if we want to solve this, the normal equations, then what do we get? We get x is equal to A transpose A dagger, A transpose B is a solution. I mean, there may be many others, but this theorem is saying that it is a minimizer. So in general, if we look back, if we express, so minimizing AX minus B is the same as equivalent to minimize X in Rn of the square, right? And we noted that this is nothing but X dot A transpose AX, and then there was a minus 2 A transpose B B dot X, and then there was a term which did not really matter. Essentially, what we have shown is for this convex optimization problem, this is a minimizer, right? The A transpose A pseudo inverse A transpose B. Okay, so this is what we're going to use for going back to a non-convex optimization problem. So let's go back to that. So I said we'll take a detour in linear algebra and come back to that. So a non-convex problem, non-convex quadratic problem with strong duality. All right, so there the question was, we didn't necessarily have a positive semi-definite matrix. So we had X transpose A, X dot AX plus 2 times B dot X for some B n Rn and A symmetric MNR. All right. And it was subject to the condition that we are looking on the unit ball, inside the unit ball. So in many cases, you can think of it as you have a certain function, you have done a second order approximation to that. And in order to minimize that function, effectively, you're trying to minimize the second order term, or in some sort of approximate sense. And here the one could be replaced by an epsilon, for example. I mean, here it's a scaled version of that problem, but one does not really mean one. You can replace it with some epsilon also. So you can talk about like minimizing a certain function by looking at or locally minimizing a function by looking at certain type of second order approximation. I mean, remember, we have already done this when we looked at the gradient. We were trying to minimize which is the direction in which the function decreases the most or increases the most. And we rephrased it as a linear problem. Instead of a quadratic, it was a linear problem. And here x dot x, the perturbation was very small. And there we found out as the first order approximation, the direction of increase is in fact the gradient, the maximum increase, and the direction of maximum decrease is the negative of the gradient. So it is in that sense. Okay, so one should be thought of as epsilon, if you will. So second order approximation to a function. Okay, so here what is the Lagrangian? What is the Lagrangian? So there is only inequality condition. So we'll just have actually one number, x lambda. So it is x dot ax plus 2bx. This is the objective function. Then plus lambda times x dot x minus 1. So minus lambda, because x dot minus x is that function. And lambda has to be positive. So this is the Lagrangian. Then the dual function is given by, and now we know what the answer is, the how to minimize this as a, okay, let me rewrite this so that it becomes very apparent. So this is nothing but x I plus lambda I x plus 2bx minus lambda. All right, so g of lambda is in fact going to turn out to be minus b a plus lambda I pseudo inverse. So now we understand pseudo inverse of a positive definite matrix, at least we understand. So this minus lambda, if a plus lambda I is positive and b is in the range of a plus lambda I. Okay, and it is minus infinity otherwise. Anyway, this minus lambda term is just an artifact of having a minus lambda. We're minimizing over x. So if a plus lambda is positive, in fact, one of the exercises in your assignment 5 was assuming that you have a positive definite thing. It was giving you this inverse, right? By minus b dot this inverse b. So that was one of your assignment problems. Here, instead of the inverse, in general, for a positive semi-definite matrix, you'll replace with a pseudo-inverse. And otherwise, it will go off to minus infinity. Because there is a negative direction, if a plus lambda is not positive, then there is some sort of negative direction, and you just think of this in diagonal form, and you choose ui to be the eigenvector corresponding to the negative direction, and you shoot it off to minus infinity. So this will go much faster because there is a xi squared term, and here you have a just an xi term, so it cannot dominate this quadratic term. So eventually it will go to minus infinity. So we know the dual function now. So what is the Lagrange dual problem? So the Lagrange dual problem is maximize minus b, a plus lambda I dagger this minus lambda, then subject to a plus lambda I bigger than or equal to 0 and b vec in range of a plus lambda I. That's the Lagrange dual problem, right? And equivalently, I want to maximize, okay, maybe I'll write it in a different page. You want to maximize I equals 1 to n. So minus I equals 1 to n, qi vec transpose b vec whole squared divided by lambda I plus lambda minus lambda, subject to lambda bigger than or equal to lambda min of a. Because lambda bigger than or equal to lambda min just means a plus lambda I is positive. And here lambda I is what? Ith eigenvalue of a, and qi is corresponding orthonormal vector, corresponding eigenvector. And since there might be some multiplicity, that's why I'll just write orthonormal. So then you choose within the same eigenspace for corresponding to the same same eigenvalue, you just choose them to be normal to each other. And here it is understood that this is infinity if lambda is equal to minus lambda I. So here note that this is in fact a convex polyhedron subject to this condition. And this is actually a convex function. You can check that this is in fact minus 1 over x is always going to be a convex function. So sorry, 1 over x looks like this. All right, so perhaps you want to check that minus 1 over x minus x. Yeah, in any case, this is actually a convex optimization problem. So the dual, and in fact, in this case, strong duality will hold. All right, so I think we are past time. So maybe I'll make again a few comments at the beginning of next lecture. But the whole idea was to give you an example of a non-convex quadratic problem, which is important, which will show up just in analogy how the first order linear approximation we needed to tell that, okay, gradient is the direction of maximum increase. And this will be essentially like what is the best approximating second order curve or surface or something like that. And for that, essentially, it was non-convex since A was not necessarily positive semi-definite, but it does it has a Lagrange dual, which is a convex optimization problem, and it satisfies strong duality. All right. So next class we will summarize the whole course, and you'll have an assignment very soon. That will be a last assignment, and then actually I'll also make a few remarks about the exam, which will mostly be based on whatever assignments you have had. So we have a pool of about 30 questions. Primarily, it will be based on that. Perhaps a question or two kind of perturbed version of those assignments. Anyway, so see you on Thursday.